Everyone, welcome to EC TechNest. Today is day 9 of the Verilog and Digital Design series. Today we'll be learning about digital comparators and introduction to test benches. A digital comparator is a combinational logic circuit that compares two binary numbers. If you have A and B, it will compare the two numbers and tell you either it is equal, greater than, or lesser than. The 1-bit comparator. For two 1-bit inputs, the logic is straightforward. If it is equal, the it will return true if both are 0 or both are 1. That is, in this condition, it will give A equal to B. This is an XNOR operation. What is the other condition? If A is greater than B, we can write true only if A is equal to 1 and B is equal to 0. For less than, you can use A lesser than B. It means A will be 0 and B will be 1. But in real world, you will not be just having 1-bit comparator, right? We will be having multi-bit comparator or n-bit comparator. In such conditions, what we will do is we'll follow the most significant bit principle. That means if A3 is greater than B3, then A is also greater than B regardless of the other bits. So MSB is given the most importance. That means if your A3 is greater than B3, it means the whole number is obviously bigger, right? A3, A2, A1, 0 will have a higher value when compared to B3, B2, B1, 0 together. So if the MSBs are equal, move to the next bit. It means consider you have 1 here also, here 1 also. So it is equal. So we'll go to the next. We'll compare these two. In these two, A2 and B2, if A2 is greater, so obviously this number becomes greater. So we go from A3, we compare A3 and B3. If it is equal, we go to A2. Even if that is equal, we compare A1, B1. So if all are equal, we can write it as A is equal to B. This is the logic that is followed. The numbers are only equal if all corresponding bits are equal. It means if all the A3, A2, A1, A0 is 1, 1, 1, 1, and here also it is the same, then we can say it is equal. Verilog code for a 4-bit comparator. You saw the diagram, right? Yeah. For a 4-bit comparator, what all do you need? You need 4-bit input, that is A, and a 4-bit input B. You need 4 output actually. One is A greater than B, one is A equal to B, one is A is lesser than B. So always at all conditions we begin. So before starting that, let us put a default condition saying that all these whatever our output is, it is 0. So if A is greater than B, if the value of A is greater than B, we'll write it as 1. So A greater than B is initiated as 1. Else if it is not greater, we'll check whether it is equal. If it is equal, A equal to B will become 1. Else, the last condition, if both these conditions are not met, we'll say that A is lesser than B is equal to 1. End the module. Introduction to test benches. Now that we have seen comparator, we'll see how to write test benches. We have also discussed about test benches in our previous videos, but not to the depth. We've just given a basic understanding what it is. Today we'll understand it in a bit deeper way. Until now, you have exactly been thinking that the code that goes inside the chip. It means we are always talking about the design part. Now, if I have completed the design, I need to test whether it is working properly or not, whether whatever inputs I am giving, that stimulus, and observe. I should observe the output, whether I am getting the required output or not. So we need test benches. The key concept in a test bench: unit under test, or we also call it design under test (DUT). It means the specific module you are testing. Module is the design. That module is getting tested here. Stimulus, the fake input signals you create to see how the UUT reacts. It means you give a number of input signals to check what will be the output. Non-synthesizable. It means when your design is synthesizable into a hardware logic, but for test bench code we cannot do it. It is just testing, right? How a simulation works. We'll take a small example here. When you run a test bench, the simulator creates a timing diagram. You define the time scale 1 nanoseconds, 2 nanoseconds, and you can tell the simulator to change values at specific intervals. So what this is called as time scale. I'll make a separate video on different types, how we can put the time scale and explain it in detail. For now, you understand, we are telling that how much, how can I tell it? Okay, I'll explain it in a different video in detail to you. For now, you understand just the time scale. For the first 10 second, 1 nanosecond, you have A equal to 0, B equal to 0, and you will check for the output. Then you will wait for 10 nanoseconds. Then you will set A equal to 1, B equal to 0. And observe if the greater than flag flips to high. It means when we wrote the code here, we are waiting after 10. First, I'll check right whether this is greater or not. Then I'll wait for 10 nanoseconds and get the output. If it is not there, I'll check for whether this flag has become high or not. If this is not the condition, if it has returned false, I'll check whether this flag is enabled as 1 or not. So, okay, for the same 4-bit comparator, we have written a test bench. Module 4-bit comparator, TB stands for test bench. So, I'll give the same input here, but I'll mention it as test bench and test bench. So, we need 3 wires, that is greater than, equal, and lesser than. Integer I and j I need it for this looping. I'll tell also why do we require looping. Now we'll instantiate the design under test comparator 4-bit. I will connect whatever have these are the inputs of my design. These are the inputs of my test bench. So I need to instantiate it. It means like connecting the design module to the test bench module. Now initial begin display. This is just a display statement that I'm using. The actual logic is here. So the thing is, when you're working on a 4-bit comparator, you will have multiple inputs around like if you exactly calculate, you'll get around 256 variations of input, right? So to sit and write everything, it will become a very tedious task. So what I will do is I'll put a loop. So my A value and B value will increment in a loop. So first I'll do it for A. I have taken a integer variable I. So if I is equal to 0 and I less than 16, I equal to I plus 1 begin. Then so till from I is equal to 0 to I is less than 16, it means 0 to 15 my loop will run. The same goes with here. So we'll get 0 to 15 for this, 0 to 15 for this, and I'll wait 5 nanoseconds. So when this loop runs for the first time, it will be A test bench is equal to 0 and B test bench is equal to 0, and I'll check for the output. What will be, which flag of this will go high? Then again I'll run this loop, it will become 1 and this will also become 1. I'll check for the same condition again. So this loop will continuously run. So all my test cases, like whatever inputs I had to check the 4-bit comparator on, this will be done by using the for loop. Then after I have finished it, when the I and j variable reaches less than 16, this loop will finish. So I'll display test as completed and finish it. End module. In the next lecture, we are also going to discuss about these kind of display statements or other. We have dollar monitor. Such things we'll discuss in the next lecture. Comparison. We have design code RTL and test bench code. We'll see. Here you are defining the hardware logic. Here you are verifying the hardware logic. This is the design, and here the verification process is going on. Hardware. This will get converted into gates and wires. This will never go out of the computer. It will just show you the waveform. For this input, what will be the desired, for desired input, what is the output you are getting? Inputs from pins to other modules will give the input. Here it's defined by your initial block. See, I have written initial begin, and this is the loop that we are running. If you have any doubts, feel free to put it in the comment section. Thank you.